Good day, everyone. From those in South Africa, somewhere in Africa, and all around the world. Good morning, good day, good evening, whichever time you'll be watching this. So, today I want to talk quickly about the photoelectric effect. Particularly, I want to just do graph questions. So, if you haven't subscribed on our channel, welcome, and please do the right thing and just subscribe. And particularly, if you've got questions in relation to anything in physics, physical science, or chemistry, you're more than welcome to hit me up. Please look out for my email on the description of this video. And by the way, please, if you like the videos, just give it a thumbs up so that we make sure that we get that algorithm running. Okay, right. Now, today, I want us just to start on the theory side on photoelectric effect. Now, if you haven't watched my previous video on the photoelectric effect, perhaps it would be wise for you to do that, because I'm just going to build on what I've already covered. Okay, so essentially, where we ended up when we started with the photoelectric effect, we started by simply saying we know that photons are emitted. So as a result, electrons are emitted. So as a result, we had an equation E is equal to omega 0 plus kinetic energy, right? So this is what we had. We said this E here, this energy here, E, is related to, in this case, the energy of photons. Okay, so we said this is related to the energy from a photon. We know that. How do we calculate that energy? We calculate this is equals to HF. Okay, this would be the frequency of light, isn't it? Okay, so omega 0, this represents the work function. We said this is the work function, and this represents essentially the metal, okay, the metal on which we are working on. And by the way, how do we get the work function? So in this case, we say HF0, where we said F0 is the threshold frequency. Please remember that. Okay, and then so we said this is the threshold frequency. Frequency. Oh, my spelling wants to run away with me a bit there. Okay, and we said, okay, this causes a maximum kinetic energy. And by the way, this has to do with the electron, right? The movement of electrons. So as a result, we know that electrons are going to move because of that. And typically, we said, how do we calculate kinetic energy? We said this is half mv squared. Okay, so this is half mv squared, where m is the mass of an electron. And by the way, you are given that mass, and the mass of an electron is 9.11 times 10 minus 31 kilograms. Okay, right, so that would be the mass of an electron. So we said when the energy of the photon is greater than the work function, the minimum energy required in order to emit electrons from a metal surface, what it does is that it causes electrons to therefore start moving, okay? And as a result, that movement, energy due to movement, is kinetic energy. Now, what I want to quickly do here is relate this to graphs, okay? So typically the type of graphs that they usually, or the type of graph that we usually have on the photoelectric effect, okay, is a graph that has to do with energy, or kinetic energy, I should say. All right, let's say energy, kinetic energy against frequency. So it's a graph that has to do with kinetic energy against frequency. Okay, and usually you get a graph that looks typically like that. Let me just explain that a little bit. So suppose we had a metal, okay, right? Suppose we had a metal, and this metal of course has electrons, and let's irradiate some light onto it. So Here's our metal. There's electrons typically in that metal, and let's just irradiate some light onto it. So what happens? We said that light has got packets of energy that are called photons. Okay, right. So if the energy of the photon is less than the minimum energy required, that is the work function, right? The minimum energy required, what happens? The electrons will not move. So electrons will just remain inside, or rather will remain on the metal. Okay, right. So in this case, we said once the energy is equal to the work function, okay, the minimum energy required. So in this case, what happens? The electrons will therefore, they will actually just lift, but they will not move, right? So in that case, that was condition number 2. So when you look at this graph, what it's typically telling you is that the frequency here, now look at this, the frequency here, right? This frequency here would be less than the minimum frequency that is required, the threshold frequency. So essentially, if that frequency is lower, right, there's no kinetic energy. Look at this, the kinetic energy here would be 0, okay? So that's your 0 mark there. So the kinetic energy here is 0, but still, let's increase that frequency again. You still find that the kinetic energy is 0, okay? There's no movement of electrons. But once we get to this point here, I want you to please note, ladies and gents, that this now symbolizes our threshold frequency, the minimum frequency required for electrons to be emitted. So when the graph cuts through the x-axis, and I'm going to show you just now from a typical straight line equation. So once the graph touches the x-axis, right, then this value here tells us about the threshold frequency. And by the way, I'm going to show you also how the gradient also represents Planck's constant. Okay, so now once we pass this value here, the minimum energy required, look at this. This frequency here, let's call it F1 for argument's sake. Okay, so this frequency here, F1, does actually now begin to cause kinetic energy. So the electrons typically at that point would be moving, and you actually would have the value of the kinetic energy there. Okay, right. And look at this. The higher the frequency, the higher the value of that kinetic energy would be. Okay, so what I want to actually just emphasize is that you can always tell where the threshold frequency is. Okay, and by the way, once you've got the threshold frequency, it means you can actually determine the work function. Okay, if you remember, how do we get work function from threshold frequency? We said you get the work function by simply saying h multiplied by f0, which is our threshold frequency there. Right, now let me relate this quickly to graphs. So what I'm going to quickly do is I am going to just change that equation around. Now, if you remember from straight line equations, you've got y is equals to mx plus c, of which this looks like that kind of a reaction. That kind of a graph, right? So if you look at this, so this looks like a straight line graph. Now, typically in mathematics, you would have y over here, you'd have x over there. Okay, right? So if that's a straight line graph, that would be your y-axis, that would be your x-axis. Now, in this case, for our y-axis, we've got ek, right? Look at that graph. So your y, which is on this side, that's your y there. So in this case, we want to have ek as the subject of the formula. So what I'm going to do is, let me change this equation around, okay, such that I've got ek. All right, now note this, if I take omega 0 to the other side, all right, so I'm left with ek max. All right, so that's ek max here is equal to E which is that energy there of the photon, minus, okay, if I take that to the other side, it changes sign and becomes minus. So that's minus omega 0. Okay, now remember what this energy is. This is HF. Okay, so E is equals to HF minus omega 0. Now, I want you to realize something here. So EK max, that's HF minus omega 0. Now look at what we've done now on this equation here. We've kind of typically made it look like this equation. Look at that. So EK max, that represents the Y. So EK max is the Y axis. So here it is. We've got EK max. F, that's the X axis. So X here. So you've got mx. So this is the gradient of your graph. So here, the gradient is represented by h, Planck's constant. So I want you to notice that on this graph here, the gradient is actually Planck's constant. And by the way, we know what Planck's constant is. Okay, it's always given to us, but we know that that represents Planck's constant. Okay, and then we have minus omega 0. So meaning, by the way, your C value on the straight line graph, this will always typically be your y-intercept. Okay, when you put the equation in standard form like that, that represents your y-intercept. Okay, right. So in this case, it means that your y-intercept is omega 0. Now, ladies and gents, I'm going to take you somewhere a little bit, but I'm also going to give a warning to that. So remember, there's no such a thing as negative energy in a sense, right? Energy is a scalar quantity first of all, right? So it's either we release energy or we absorb energy, right? So we know that energy cannot be created or destroyed, but it's transformed from one form into another. So I just want to take a different color here so that I can extend this graph. Now notice I'm going to now take this graph into the negative energy region. Okay, right. So in this case, when I extend this graph over here, right, look at that. Now it touches on the y-axis, but it's on the negative side. So in real life, this portion over here does not exist, and that's why I've drawn it in a different color, and that's why I've drawn it as a dotted line. It really typically doesn't exist because there's no such a thing as negative kinetic energy, right? So now I want you to please note, we said at this point here, electrons are not moving, right? So electrons would still be stationary, okay? So at this point here, only at the threshold frequency do we start seeing some movement, and after that, when the energy is greater, when the frequency is greater, the energy is greater, and therefore there's some movement that's happening here. However, the reason why I'm mentioning the omega 0 part, we said this now represents the y-axis. Yes, the y-intercept instead, right? We said the C here usually represents the y-intercept, meaning when you extend this graph, on this portion here, you'll actually have your work function over there. Okay, remember, that's the y-intercept there, and there it is there. When I extend, there's my y-intercept where it cuts the y-axis. Okay, so it means this value here would actually represent the y-intercept. Okay, right. So typically this is the most popular graph when it comes to photoelectric effect. Okay, and as a result, most of the time you will find that you are given this kind of a graph. So what I want to do quickly is, having just gone through the theory a little bit, okay, what I'm going to do is, let's just take a past exam question and show you how to apply this theory. Is that good? Fantastic. Let's go. All right, so I'm going to take a question paper from September 2019. That's from the Free State. Okay, so this was a prelim, as some of you are preparing. Um, so in this question, they say in an experiment that they say light of different frequencies is shone onto a photocell, right? One with a cesium cathode and the other one with sodium cathode. Now, please, I want you to note in this case, they gave you two different metals. And as a result, remember that because we've got two different metals, it simply means that we'll have two different work functions, right? Remember, I did state in our previous video on photoelectric effect that each metal does have its own work function in a sense, right? Now, they say the sketch graph of frequency versus kinetic energy of the emitted electrons is shown below. So there they give us those graphs there. So I want you to notice what they did on the graph. Do you see that portion there that they drew in dotted lines? Okay, right. Let me just get that closer. So they drew that portion as a dotted line so that you could actually see that this part in real terms does not exist. Okay, so remember, between this point and that, it means that let's take for cesium, for instance. So between that point and that point, it means that electrons are not able to move. Okay, so as a result, the kinetic energy of the electrons is zero. Okay, remember, it cannot go to the negative, but we are extending it here because I showed you that's where we are going to get the work function. Okay, right. And then for sodium, okay, so it means that electrons would be zero at this point until we get to that portion there. Okay, it cuts through the x-axis, or in this case where we start having some movement there, and then kinetic energy starts increasing. All right, now quickly let's just answer the questions that they've given us there. Okay, they say define the term threshold frequency or cut-off frequency, or by the way, that's another word that they use for the threshold, the cut-off frequency, right? We said it's the minimum frequency required to emit electrons from a metal surface, right? Right, they say which photocell, okay, will for the same frequency of light emit photoelectrons with higher kinetic energy. Choose from cesium or sodium. I mean, that should be quite simple to see from the graph. Okay, they said for the same frequency. So suppose you take any frequency there, right? I just want to typically show that. Let's say we choose a frequency there. Okay, so if I choose a frequency, that will be the kinetic energy for sodium. Okay, but look at that. For the same frequency, okay, I'll get a higher kinetic energy for cesium. Why? Because it has a lesser work function. You can see that the threshold frequency, it uses less energy. It needs, or it requires minimum a lesser amount of energy in order for electrons to be emitted, right? So they said I choose between cesium and sodium, so definitely that will be cesium there. Okay, right. They say name the energy value shown at A, which is that value there. Okay, so you already know that should be the work function, isn't it? Okay, so that tells us that should be the work function. Okay, so they say write down the name of the quantity represented by the gradient of this graph. You see, we've answered all of these questions already, ladies and gents. Okay, so the gradient of the graph, that is Planck's constant. Okay, and then now we're going to get into the calculation part of it. Okay, they say for a certain frequency of light, the maximum kinetic energy of the photoelectron from sodium is that amount. So they gave us the kinetic energy, right? And they want us to calculate the wavelength of the light used. Now, ladies and gents, Remember, we said the equation that we're going to use, okay, I'm just going to use a different color there. The equation that we're going to use, okay, is as simple as this. We know. Oh, by the way, just to show you, that equation is actually given. It's just that in the form that it's represented in, it might look a little bit daunting. There it is there. E is equals to omega 0 plus Ek, that's Ek max. All right. Okay, so that's the energy of the photon, the work function, and the maximum kinetic energy. Remember, this has to do with the electron. So you are given all of that in your data sheet. Okay, right. So we know that we're going to use our equation. So E is equals to omega 0. Okay. Right. So I'm just going to put that in the short there. Okay. So that's E is equals to omega 0. Okay, plus Ek max. So that's kinetic energy maximum. All right. So now we know that we wanted to calculate the wavelength of the light that was used. So which one has to do with the light? It's this guy over here. But we already know, okay, that's hc over lambda. Right. If you are confused about this, okay, please just refer to my video, my previous video on the photoelectric effect. We know that E is equals to HF, but we know that F is C over lambda. Okay, so in this case now, where are we going to get the work function? Remember, when we look at our graph, okay, that value there where it cuts. So they said for which metal? We have to be very specific. They said for sodium. So for sodium, the work function, we are given the threshold frequency to be 5,31, but please remember, this is times 10 to the power 14 hertz. Please don't forget this part, because typically they like doing that, okay? Putting obviously the factor just on the axis there, right? So this would be H. I'm going to use, because we are not given the work function, but we are rather given the threshold frequency. So omega 0 will be HF0. This has to do with the metal. And we said plus Ek max. Now, obviously, I was going to write this as half mv squared if we were given the speed of the electron, but we're not given the speed. Rather, they gave us the maximum kinetic energy. Okay. Right, so now let's substitute all that we know. That's 6.63. That's Planck's constant times 10 minus 34. By the way, remember, you are also given that constant just to show you quickly. All right, those constants are always given to you. Okay, so there's our constant there, Planck's constant. There it is. That's 6.63 times 10 minus 34 joules seconds, right? Okay. So multiplied by the speed of light in a vacuum, that's 3 times 10 to the power 8, divided by the wavelength. But that's what we are looking for, isn't it? So we're looking for the wavelength. And this is equal to, now please, I want you to note, we've got F0 there. So we're going to just simply say this is 6.63 times 10 minus 34 multiplied by our F0 value is 5,31. So it's that value over there. That's the threshold frequency. Okay, so this is 5.31 times 10 to the power 14. I just showed you why that is the case there. There's our scaling factor over there. Okay, so what is this going to give us? It's going to give us, we're going to add the maximum kinetic energy to that. Okay, and remember, we're given that value as 2.03 plus times 10 to the power minus 19. So this is added 2.03 times 10 minus 19. Okay, right, now all we need to do is just calculate our wavelength there. Okay, this will be a bit of a working out, but please, ladies and gents, we shouldn't be spending a lot of time on those calculations over there, right? So I'm just going to pull out my calculator quickly. Okay, so what do we have? I'm just going to start with what's on the right hand side. So we've got 6.63 exponent minus 34 multiplied by 5.31 exponent, sorry, that's not minus there, so that's times 10 to the power 14 plus we've got 2.03. Okay, so I've got 2.03, that's minus 19 times 10 minus 19, and I get a value there which is 5.55, okay, times 10 minus 19. So I'm just going to retain that value over there. Okay, now what you would have, all right, because I know some of you would complain about the mathematics involved here. Okay, so what you would have is that over there, so 6.63 times 10 minus 34. And if you're struggling with this, ladies and gents, please just make sure you get your maths right. Okay, over lambda, which is 5.55. I wouldn't advise for you to actually round off at this point, but if it will make your maths easier, perhaps it would be best to do that. Now please remember, we're going to cross multiply. Lambda multiplied by that, okay, would be that multiplied by lambda. Okay, and then obviously we've got that product there. Okay, and ultimately we're going to divide this with the 5.55. So all that I will have is, I'm just going to do that quickly. So that's 6.63 minus 34. Okay, maybe I should have put that in brackets. Okay, multiplied by 3 exponent 8. Okay, so you can do that for yourself. See if you get an answer there. All right. Okay. All right, I get an answer of so 3.58. So please try to work that out on your own. So that's 3.58 times 10 to the power minus 7 meters. That's the answer that I get to. Okay, please try to work it out on your own. Of course, you can try with whichever method that you would prefer in terms of the maths, but as long as you understood. By the way, ladies and gents, don't spend too much time on the working out here, because in actual fact the physics just ends there. This is all mathematics, right? So all we wanted was to get the wavelength over there. Right, now let's get to the last part of this question. Okay, just to show you that it's actually quite doable. Okay, then they ask the question, what influence will the following changes in the incident light have on the maximum kinetic energy? So we're going to make changes on the light itself, right? And we want to know how will it affect the kinetic energy, right? They say choose increase, decrease, or remain the same. Okay, stays the same. They say, right, so the first change is an increase in the wavelength of light used. Okay, so what will happen when we increase the wavelength of the light used? So what I'm just going to do is just show you over there. So remember, the energy of the photon is HF, meaning when I increase the frequency, I increase the amount of energy. And once I increase the amount of energy, okay, the kinetic energy will also increase, right? but now they said we increase the wavelength. So in this case, that's hc over lambda, which is our wavelength over there. Okay, now this wavelength, when we increase the wavelength, which is what they asked us to do, remember it's in the denominator, isn't it? So once I increase the wavelength, I increase what's on the denominator. What happens to the energy? The energy will decrease. Okay, so when I decrease the energy, that will decrease the kinetic energy, and that's our answer, right? So our answer for this one, it will decrease. All right, so in this case, an increase in wavelength will decrease the amount of energy. All right, or you can say the decrease in wavelength increases rather the sorry an increase in wavelength rather, okay, will decrease the frequency, which will decrease the amount of energy that is required. Okay, and as a result, kinetic energy decreases. Right, so and then the final part of the question, the last part of our question, okay, they say an increase in the intensity of the light used give so now they're increasing the intensity. Now if you don't know what intensity actually stands for, again I'll say to you, please watch the video that I've already produced on this, on the photoelectric effect, and you'll see that I did quite a concise explanation of it. Okay, it will help you quite a lot. Right, so they say an increase in the intensity of light used, give a reason for the answer. Remember that an increase in intensity, right, we said that's an increase in the amount of power that the light has, right? That's the increase in the brightness of the light. Okay, that will not have any effect on the kinetic energy. Yes, it will have an effect on the number of electrons that are emitted per second, but it will not have an effect on their kinetic energy because the frequency would still be the same. So as a result, ladies and gents, the answer to that is it will remain the same. Okay, stays the same. So that's the option that we're given. Okay, so stays the same. So as a result, if it stays the same, then we know they said give a reason for your answer. Okay, because in this case the frequency remains the same, and as a result the kinetic energy would remain the same. All right, so I want to just leave it there. Okay, perhaps when we do our revision, we'll do some more questions on graphs. I hope that's been really fruitful. Thank you so much, ladies and gents, and I wish you all the best for your exams as you prepare. Okay, and I'll see you again next time. Thank you. Sharp, sharp.